Hey everyone, this is Derek, and this is video 3 of 3 for the first derivative test. And we've actually arrived at the first derivative test. And so what we're going to use this for is finding relative minima or maxima. And so like in the last video I was talking about, we have where things are increasing and decreasing, increasing. And then we have these critical points right here, or critical values. We're going to discover the critical points. And then what they're going to be is either local, or sometimes they use the word relative. I'll probably end up calling it local mins and maxes. But so this would be like a local max right here, and this would be a local min. And so overall, it looks like this function goes to infinity on either side, but often these points are of interest. And so that's what the first derivative test helps us find. So if we know what the signs are of f prime, which is the increasing, decreasing, then we actually do already know if it's a min or a max. So in the previous video we made the little sign chart, and we would have said it was increasing on this side and then decreasing on this side of a 0. If you think that means the slope was positive and then it went to negative, and so that has to be a maximum. If your slope was negative and then it goes to a positive, well, that's gonna have to be, this should be minimum right here. And then we could have a thing where either the slope's going up both times or down both times, and that's something like x cubed, where it kind of comes in, flattens out, and then goes back up. And I didn't draw it very good, but right there, there's this little spot where it just momentarily flattens and becomes 0. So that's where you have these, and you can see it's not a min or a max. Okay, so for this question, we'll use the first derivative test to find the relative maxima and minima for the function. So here's our function. Our first step is going to be to find f prime. Let's go ahead and do that. So 3 times 1 makes 3, and then take 1 off. And then here, 3 times, this would be like 2 times 3 over 2. So those will just cancel. And that's going to get us a nice 3x right there. And then our next step in the first derivative test is to find anything that makes this 0 or undefined. And since it's a polynomial, there's no undefined values. So we'll just set it to 0, and then we will factor. It looks like it's going to be the way to go here. So we'll take out a 3x, and that will leave me an x minus 1. And so it looks like our zeros are going to be x equals 0 and x equals 1. Now that we have that, we'll make our little number line. So these are going to be our critical values. And we'll put f prime up here, and we'll put x down here. And so I have 0, and then I have 1. So for my test points, I'll do maybe -1, 1/2, and 2. And so these are both places where the slope is 0. So if I put a -1 in here, this would be negative times negative, so that's positive. Notice it's easier to plug it in the factored version than up here. If I put in a 1/2, this will be positive times negative, so that's negative in there. If I put in 2, that'd be 6 times 1, so that'd be a positive. And so then if we go back to our chart, it's right back here. So when we go positive to negative, so positive to negative is a maximum because we're increasing and now we're decreasing. So that means this point right here will be a max. And then when we go negative to positive, so that means the slope was negative and then it's going positive. So then this point will be a min. And then we just have to figure out what the other half of the coordinate pair is. So right now we know that we have an x of 0 is going to be one of our turning points. That one's going to be a maximum, and we'll have another one at 1. So I'm just going to put 0 back into actually the original function up there. So we'll find f of 0, and then 0 minus 0 is just going to be 0, right? So that means we have a max at 0, 0, or a local maximum, or relative, I guess, in this book. And then we have another critical value at 1, so we'll plug that back in to the original, and that will give us 1 cubed minus 3/2 times 1. So 1 minus 3/2, and that is -1/2. and that was f of 1. And so that means when x is 1, y was negative 1/2. And that was that was a minimum, a local min. So that would be a relative minimum and our relative max. Okay, some directions. So this is our function now, and we're gonna, that 16 over x, it's easier if we write that as 16 and x to the negative 1 plus 9. So we'll think of it this way. Let's find our f prime. So this is like 1 times 1, and then minus 1 would be x to the 0, so just a 1. This would be negative 1 times 16, so I'll make a minus 16x, and then take 1 off the exponent, so that gets us to minus 2. So there is our derivative, and then, oh, on this one, I should probably make the note right here that x cannot equal 0. So this one actually does have a domain restriction. And so when I come down here, in my critical values, if I happen to come up with x equals 0, it doesn't count because it's not in the domain of the original function. So we'll do 0 equals 1 minus 16x to the negative 2. Let's bring this over. So that's going to be 16x to the negative 2 equals 1. This is really that. And so I'm going to think of it as multiplying both sides by x squared to clear the fraction, and then those cancel. So now I have 16 equals x squared. And then careful right here, it's really easy to get x equals 4, and it's not. It's when you take the root of both sides like this, you need a plus or minus on that side. So this is actually going to be equals plus or minus 4. Another way of looking at that is if I took this and brought that 16 over, I would have 0 equals x squared minus 16. And now if I factor x plus 4, x minus 4. So you can see we totally do need both roots. So now that we know our x values, those are our critical values of 4. And in our derivative, we are supposed to check for, can the derivative, does the derivative have anywhere it's undefined? And it does. My derivative has a 16 over x squared, so it's undefined at x equals 2. So that's a potential critical value, but because it's undefined in the original function, it doesn't count. So now we just need to figure out kind of what the signs are doing, and then do we have mins or maxes? Okay, so I set up the sign chart over here. And so our zeros were negative 4 and 4, so I'm going to use negative 5, 1, and 5 to check my intervals. And then up here is my first derivative. So if I put negative 5 in there, that would be 16/25, so 1 minus 16/25. That's 16/25 is less than 1, so that'd still be a positive value. If I put 1 in there, then I end up with 1 minus 16, so that'd be negative. If I put 5, again with the 16/25, so that would stay positive. Okay, so then what we'll do is we'll take our critical values, x equals 4, and then next x equals negative 4, and we'll put those back into the original function, and then get our mins and our maxes. So if I put in 4, f of 4 is going to equal 4 plus 16 over 4 plus 9. So f of 4 is 4 plus, that'd be 4, and 9 is 17. And so that means we have the point 4 and 17. And that one is going to start off with a, let's see, where are we? On 4, that was going negative, right? And then positive, so that one would be a min. And we'll do the exact same thing with x equals negative 4. So plugging in negative 4, I have negative 4 plus 16 over negative 4 plus 9. That would be negative 8 and 9, so that would be a 1. That was f of negative 4, bad notation there. And so that means when x was negative 4, y was 1. And that one started off with a positive slope and then became 0 and then had a negative slope. So that one would be a max. Okay, same directions on this one. Find if any relative max or mins of the function. So here we need to make the note that we have a domain restriction that x cannot equal 4. So even if that comes up as one of my critical values, it doesn't matter because it's not in the domain of the original function. So it won't be a min or max because it's not here. So I'm gonna do the derivative this way. Right? I could do quotient, but this is easier. So let's do that general power rule. So for f prime, we'll go negative 1 times 3 for negative 3, x minus 4, and then we're just taking 1 off of that, so that will make a negative 2. And then we do have to multiply that by the derivative of the inside, but that in this case is 1, so it doesn't affect the problem. This, if I write this in a little less of a mess, 1 times negative 3, that's going to be negative 3. And then this has a negative exponent, so I'm going to bring it into the denominator, because remember when we have a to the negative x, that makes 1 over a to the x. And so this will be x minus 4 quantity squared. And so here, there's nothing, if I set this to 0, multiply both sides to clear the denominator, I'm just going to get negative 3 equals 0. So there's no 0, so that's not going to contribute critical values. And then we also have to check points that are undefined, but that would be x equals 4 again, and we already set up here that x doesn't get to be 4. So this one just does not have any maxes or mins. So that's the situation. Or it it goes to infinity. I should be a little careful how I say that. It doesn't have local maxes or local mins. What this graph ends up looking like actually is we have a kind of an asymptote at 4, and on one side of that it'd be going down to infinity, and on the other side up. So there's no kind of local bumps or valleys to identify.